1,000 lakes inside a desert every single year. Sand doesn't hold water. Hydrology is unambiguous about this. Welcome to the science of the unexplained. I want to take you into the space where a rule breaks and nothing explains it. Every year, roughly 1,000 crystal-clear lakes materialize inside one of South America's largest dune fields, a place that receives no rainfall for 6 straight months. Hydrology has a rule: sand doesn't hold water. Sand is porous. Sand drains. That rule is not wrong. So how is it that satellite images from August show a desert filled edge to edge with lakes so blue they look painted? The question isn't where the water comes from. Scientists settled that decades ago. The question, the one that keeps hydrologists up at night, is why the system that creates these lakes is, by every physical measure, one catastrophic dry season away from never forming them again. Lençóis Maranhenses National Park sits at the northeastern tip of Brazil, where the Atlantic coast bends sharply westward into Maranhão state. The park covers approximately 155,000 hectares, a figure from ICMBio, Brazil's federal conservation authority, and from the air it looks like a crumpled white sheet, which is precisely what its name means, asterisk the bedsheets of Maranhães. Dunes rise as high as 40 meters, their faces steep enough that a person sliding down them picks up speed. Nothing about this landscape says water, but the rainfall data from INMET, Brazil's national meteorological agency, tells a different story. The region receives roughly 1,600 millimeters of rain per year, nearly all of it concentrated between January and June. That is more annual rain than London. Here is the contradiction that should stop you cold. The rain falls, the lakes form, the dry season arrives, and then the lakes vanish completely. For months, the landscape is pure sand, no puddles, no traces. Then the rains return, and the lakes reappear in almost exactly the same places. Not nearby, the same places, but repetition is what forced scientists to look beneath the surface. Because lakes don't reappear in the same location by accident. Something is controlling where they form, something hidden, something structural. And when CPRM, Brazil's Federal Geological Survey, began mapping the subsurface of the region, what they found didn't simplify the question, it made it stranger. The sand at Lençóis Maranhenses is not ancient. Geologically speaking, it is recent. Quaternary deposits driven inland from the coast by persistent southeast trade winds. The dunes migrate, they move. A dune that existed in one position in a given decade may occupy different ground in the next. This is normal dune behavior, and it is important because it means the surface of this system is in constant motion. Beneath that motion, however, lies something that does not move. CPRM's hydrogeological surveys of the Maranhão coastal zone identified a basal aquitard, a layer of consolidated rock and compacted sediment running beneath the mobile sand. Aquitards are impermeable. Water cannot pass through them downward. In most landscapes, this kind of layer sits too deep to matter. Here, it sits close enough to the surface that rainwater percolating down through the dunes hits the aquitard, stops, and has nowhere to go. The water pools. In the low corridors between dune ridges, the interdune swales, it collects until it becomes visible. A lake. This is the mechanism. It is not exotic. It is not controversial. Perched water tables above impermeable layers are documented across dozens of geological systems worldwide. The physics is introductory level hydrogeology, so why did it take so long for anyone to apply it here? Because the landscape looks like a desert, and deserts are not supposed to have perched water tables close enough to the surface to form visible lakes. The visual evidence, white sand, no vegetation, brutal dry season, trained every observer to assume the water simply evaporated or drained. The aquitard was invisible, Nobody looked for it because the surface said there was nothing to find. But here is what the aquitard explanation does not resolve. If the layer is impermeable and the geometry of the dunes channels water into the same interdune corridors every year, then the lakes should form reliably, predictably, stably, year after year, same depth, same duration, same distribution. They don't. Lake depth varies by meters between wet seasons. Some lakes persist into September or October, others vanish by August. The spatial pattern shifts. In years with below average rainfall concentrated in fewer weeks, the lakes are smaller and shorter lived. In years with extended wet seasons, some lakes connect into channels. The aquitard is fixed. The dune geometry is roughly fixed. The variation in the lakes is real and measurable, and the fixed elements of the system cannot account for it alone. Something else is modulating this, and identifying that something required researchers to stop thinking about this as a geology problem. The variable the geology couldn't explain turned out to be temporal, not spatial. Researchers studying the hydrology of the Maranhão coastal zone, including work published through Brazil's federal water resources programs, identified that the lake's behavior depended not just on how much rain fell, but on when it fell relative to dune migration. The dunes are not stationary. Their movement, driven by the southeast trade winds, continuously reshapes the interdune corridors where water collects. A corridor that was 30 meters wide one season may be 22 meters wide the next as a dune advances. A shallower corridor holds less water, drains faster, disappears sooner. This means the system has two independent clocks running simultaneously: the hydrological clock, rainfall timing and volume, and the geomorphological clock, dune migration pace. The lakes are the product of both clocks aligning, and neither clock is synchronized with the other. Geographer Iris Rocha Moreira, in research on the geomorphological dynamics of Lençóis Maranhenses, published through the Federal University of Maranhão, UFMEA, documented how dune mobility directly affects the persistence of interdune lakes. Her work, along with complementary CPRM hydrogeological mapping, established that the system is not self-regulating. It does not trend toward equilibrium. The lakes appear stable to a casual observer across a decade, but the underlying variables are moving in directions that are not coupled to each other. Here is where the question turns genuinely unsettling. Climate projections for northeastern Brazil, including analyses published by INPE, Brazil's National Institute for Space Research, indicate that the region faces increasing rainfall variability. Not necessarily less total rain, but rain arriving in shorter, more intense pulses with longer dry intervals between them. For most landscapes, this is a gradual stress. For Lençóis Maranhenses, it is a structural threat. The lakes depend on sustained percolation over weeks, not intense bursts that run off before reaching the aquitard. And the trade winds? Modeling work on atmospheric circulation in the tropical Atlantic, including studies drawing on reanalysis data from NOAA and ECMWF, suggests that wind patterns driving dune migration may intensify under warming scenarios. Faster dune migration means faster corridor reshaping, the geomorphological clock accelerating while the hydrological clock becomes less reliable. Two clocks, both destabilizing in opposite directions. The scientists who understand this system best are careful about predictions. The aquitard will persist. The dunes will continue to exist, but whether the specific geometry that allows lakes to form in those specific corridors, with enough volume to persist long enough to be visible, that is a question that cannot be answered by looking at the surface. And the honest answer, from the researchers who have mapped this most carefully, is that we do not yet have models precise enough to say when or whether the balance tips. Here is what this system actually teaches us. And it is not about sand or water. For decades, anyone looking at Lençóis Maranhenses saw either a paradox or a miracle. The lakes appeared, science eventually explained them, case closed. Accept the explanation, a buried impermeable layer, dune geometry, seasonal rain, describes a mechanism that is functional only within a narrow band of interacting variables. Remove one, shift one, accelerate one clock relative to the other. The mechanism still exists, the aquitard remains. The dunes keep moving, but the lakes stop forming. The explanation didn't solve the mystery. It revealed that the mystery was never about the lakes at all. It was about how many natural systems we call stable are actually doing something far more precarious, holding a shape that depends on variables moving slowly enough that we never notice them diverging. Lençóis Maranhenses has existed in a recognizable form for thousands of years. That duration feels like permanence. But if CPRM's subsurface data and UFMA's geomorphological research are both correct, and there is no reason to doubt either, then what we are looking at is not permanence. It is two independent clocks that have not yet gone out of sync. If dune migration rates and rainfall pulse patterns are both shifting but in different directions, is the continued existence of the lakes evidence that the system is resilient, or evidence that the divergence hasn't yet crossed the threshold we'd recognize as collapse? Somewhere else in the world there is another system holding the same kind of balance, and we haven't mapped what's beneath it yet.